Welcome! I am Panagopoulou, Virtualization Engineer at Virtual Open Systems. In this webinar, I will talk about the virtualized runtime environment in the scope of the EVEREST project. In the first place, the runtime environment of the EVEREST project will be set up in a way that it unveils the usage of many heterogeneous and distributed resources. Among others, having virtualization support is part of the solution. After all, virtualization is the key to have diverse operating system environments coexisting on the same underlying hardware. This webinar mainly emphasizes the results of the virtualization activities of the EVEREST project from the beginning till now. We will start by describing the virtualization requirements of the project and the main incentives. Then we will talk about the challenges that SoC-attached FPGAs present and provide a detailed presentation of the activities done to address those challenges. Next, we will include a simple demonstration of the FPGA virtualization work, which will run on a Xilinx MPSoC board. Finally, we will close the presentation by providing an overview of the next activities, with description of PCI-e attached FPGA virtualization challenges. Before designing any solution, there was a main question that we had to answer. How should we best integrate the benefits of virtualization on the runtime environment? In a system like this, with various different kinds of technologies, the answer became kind of straightforward. We have to keep in mind that any software application should access and use equally the heterogeneous hardware resources. In order to abstract the hardware, the virtualization solutions will be based on the KVM hypervisor. Also, they will target different types of CPU architectures. The EVEREST project greatly relies on FPGAs for some computations to be done optimally. That's why we decided to give our focus on the FPGA devices and also target different FPGA technologies. The main focus of this presentation is SoC FPGAs virtualization, which also constitutes the first part of the development activities. In recent years, ARM processors have become more and more popular. ARM SoCs often come with FPGA devices attached to the same board. It is a flexible and efficient architecture which allows the FPGAs to handle specific workloads while the CPUs handle general-purpose tasks. In this context, porting key technologies on ARM devices is of interest nowadays, and so is the virtualization of the FPGA resources. In this talk, I will describe a solution that aims to provide the advantages of virtualization in SoC-attached FPGAs. The activity mainly targets the Xilinx ZCU102 board, but is by no means specialized for it. There are many challenges in what concerns the FPGA virtualization for ARM. When we talk about FPGA virtualization, this means to provide a way for the FPGA APIs and resources to become available for virtual machines. One way to see the problem is to describe it as a twofold. In the end, guests should be able to both program and make use of the FPGA resources. Till now, there is no way to trigger FPGA programming requests from inside guest systems, and this will be the innovation of the current activity. As for the utilization of the resources, we try to set up a simple and effective way using existing technologies. So, new design as well as orchestration of existing solutions are part of the activity and both contribute to the achievement of our final goal. The solution we developed is a combination of a new component called virtio-FPGA and QEMU VFIO. Virtio-FPGA is the technology that allows the FPGA programming to be carried out from guests whenever needed. This basically gives to guests the ability to reconfigure FPGAs in a transparent way. From the other hand, with VFIO pass-through setup, guests are able to exploit the configured FPGA resources. They can then make use of them in a safe way and also without any further alterations, as if they were a host system. To proceed into some details, the virtio-FPGA component introduces the creation of a new virtual device. So QEMU creates the virtual device, called virtio-FPGA, and assigns it to the guest. This device can accept FPGA programming requests that arrive from the guest system. One can do this by using a corresponding guest kernel driver. In simple words, we developed both the new virtual device on QEMU and the guest kernel driver. So, QEMU will boot and present the device to the guest. Then, we can load the guest kernel driver, and after we do this, we will be able to initiate FPGA programming requests while inside the guest. QEMU really is responsible to fulfill those requests by interfacing with the actual FPGA hardware. It is able to do this by utilizing the Linux FPGA Manager API of the host. The FPGA Manager core exports a set of functions for programming an FPGA with a bit stream, and is also manufacturer agnostic. For the manufacturer specifics, these are hidden in a lower level driver, which in our use case will be the ZynQMP FPGA Manager. The Virtio FPGA solution is conforming to the VirtIO protocol, which achieves low overhead in the overall communication. Soon after FPGAs are configured, the guest should be able to utilize their resources. It is VFIO that comes to the save. This technique, in combination with QEMU KVM, enables direct pass-through of devices to guests. VFIO is actually a framework that is based on the IOMMU controller and allows devices to be used from a user space context. QEMU, which also lives in the host user space, is implementing this API. The untouched guest kernel driver for the device traps to QEMU, and with the VFIO protocol, it is able to safely use the host device. We have faced an issue that is worth mentioning during the integration of the VFIO solution into the picture. For ARM FPGA devices, each and every device should be pre-assigned to guests at the moment of their bootup. The reason behind this is because the VFIO platform driver of QEMU, which will be used for our kind of devices, does not provide dynamic hot plug capabilities, as it happens for instance on x86. This comes, however, in contrast to the dynamically programming logic that we would like to support. Until the hot plug feature is implemented, we can take advantage of device tree overlays in the guest. The device tree overlays are basically patches for the base device tree that can be applied while the system is up and running. With them, we can enable the candidate devices inside the guests only after FPGA's configuration. After this, the FPGA devices can be safely probed to their drivers and used. Let's see now in practice what are the capabilities of the solution. In the demonstration that follows, we will see the FPGAs being programmed and utilized by a QEMU KVM guest on ZCU 102. This platform has a quad-core Cortex-A53 and a dual-core Cortex-R5. It also features a 4GB DDR memory attached to the processing system and a 512MB DDR memory attached to the programmable logic. In the demo, first we will do some necessary configuration steps on the host. Then we will see that guest boots with virtio-FPGA and VFIO devices assigned. From the guest, we will then trigger a request to program the FPGAs and apply a device tree overlay to enable the VFIO devices that are now part of the hardware. As a final step, some testing will take place on the available FPGA device. More specifically, in this demo, we will make use of a bitstream image generated by VFIO that leverages a CDMA AXI device on the FPGA hardware. During QEMU bootup, both the virtio-FPGA device and the CDMA AXI device are assigned to the guest. Then, FPGA configuration will be triggered by the guest, followed by the device tree overlay application, which will set the CDMA device status to enabled. Finally, we will see the Xilinx VDMA driver probed to the device, and we will run a test. The test we chose is already part of the kernel for testing this kind of DMA devices. It is known as DMA test module. So let's now proceed to the actual demo. Before booting any guest, we have to do some configuration steps on the host side. This includes the application of a device tree overlay in the host system for the future FPGA devices to be able to be passed through on the guests. The overlay looks like this. And is located under the lib firmware directory. It basically, for our use case, describes a new CDMA device and assigns it to the IOMMU subsystem. Let's proceed into the application of this overlay. After this, some kernel messages, which are basically innocent, pop up, and we can understand that the overlays are now part of the device tree. Next thing for us is to bring the VFIO platform driver into the picture. To do this, first we have to set up some parameters in order to enable the VFIO IOMMU support. Then we can install the driver in the system. Finally, we have to bind this VFIO platform driver with the CDMA device. Final message, we see that the device is added to the IOMMU group. So we are now in place of booting a guest image. QEMU parameters should include both the virtual FPGA device and the pass-through device. which is the CDMA one. We are now inside the guest, and first thing we have to load the VirtIO FPGA driver that will enable the interface to do FPGA programming requests in the virtual device. And now we can trigger a request. We wait a bit. We see this kernel message, and on the host side we see this successful kernel message. Now another thing to do is to apply a device tree overlay on the guest this time to enable the FPGA device, the CDMA device, that is now part of the hardware. The overlay looks like this. Basically, it sets the status to OK for this device. We can see a kernel message that indicates that our device is probed with the Xilinx CDMA driver. Now we can run a DMA test to see whether the DMA device is indeed accessible. We will run this script that sets some parameters for the DMA test kernel module. We see that all the tests pass, and we also obtain some metrics. This demonstration basically revises the virtualization work done for SoC attached FPGAs. In the scope of supporting hardware heterogeneity, our next development effort will focus on another type of FPGA devices. We are talking about the PCI-e attached FPGAs, and we have as a development target the Xilinx Alveo board. Our goals are two-sided. From the one hand, we aim to improve the ability to attach and detach FPGA accelerators to virtual machines. From the other hand, we would like to render the SRIOV support more flexible than it currently is. To sum up, we have as a target a flexible utilization of SRIOV technique that will permit high-speed attachment of accelerators to VMs. We have as granted that the bitstream configurations provided by EVEREST SDK will include the number of virtual functions to be created. Also, using what we call the EVEREST SRIOV FPGA Manager, the virtual functions can be attached to virtual machines dynamically after their boot up. This way, the cache resources will be reconfigured. Talking about our next steps, the target is to build a PCI-e specific FPGA virtualization framework, which will enable virtual functions attachment and detachment to the VMs in a flexible way. Of course, this framework should be finally integrated and become part of the EVEREST SDK. So this is it. This is the status of the virtualization activities of the EVEREST project. Thank you for your attention.